In the next section, I want to talk about Huffman codes, which is another type of character encoding, but a much more structured and well-defined way of obtaining these codes than the ad hoc versions that we've seen up to now. Again, the whole goal in this part of the unit is to exploit different frequencies of characters. And the goal should be to find an encoding that produces short code words for frequent characters and longer code words for infrequent characters, so that the total length of the coded text is small. I'll fix the coded alphabet to be binary, so all the code words are just bit strings, which means we can just write sigma for the source alphabet because there's only really one alphabet that is changing. Now, if you take English prose, some averaging over whatever English prose is, it probably differs a little bit between different authors, but a rough approximation is given here. Some letters occur more frequent than others. So this is ignoring base, so ignoring the case. E stands for small e and capital E, etc. So you see that E is much more frequent than the other characters, and then the others follow in this order. Now, I happen to know that in German the order is a little different, so this is really language specific, but it also happens that E is the most frequent character. And you see there's some characters that even if you combine all of the last row together, this will be not much more than a single character from the first row. So there's really a good bit of uneven distributions in the character frequencies. Huffman coding is a very, very structured way to exploit exactly this. So as a computational problem, it's formulated as follows. We have an alphabet that we're given and weights for all those symbols. So the weight is just a function that assigns to a character a given number. And we will usually use the frequencies in a given text as the weights for our Huffman codes. If the text is generated randomly, you could also take the probabilities for those characters. Those two things are essentially the two sides of the coin. Now, given an alphabet and weights for those characters, the goal is to find a prefix-free code, so a code trie in other words, because that's the type of codes that we like, that minimizes the size of the coded text in the sense that if you sum up for all the characters the length of the code word times the weight of this character, this sum should be minimized. Now, why is that a good definition? Why is that the right thing to make small? If we use as weights the number of occurrences of a character in a given text, then this is exactly the size of the output. That's the length of the coded text. So in a sense, we're asking for the best possible character-wise encoding of a given text. That's an instance optimal algorithm, if you like. For any given text, it produces the best possible code. Man, that sounds quite ambitious. So you might even question if that's possible at all to compute such an optimal code efficiently. But amazingly, it's actually true. It's actually possible. You can do this. And the reason why intuitively this fairly ambitious task is solvable is that we can apply a greedy approach here. So a simple heuristic to get a best start at the solution is good enough to produce a globally optimal solution. You'll maybe figure out what this means in context if you go through the details of the algorithm. I also mentioned this term because greedy algorithms is a general class of algorithms that play a major role in some fields of optimization algorithms. I want to point to this in case you've heard about this. If you've been in the Advanced Algorithmic Techniques module, this should be familiar. If you haven't heard about greedy algorithms, don't worry, we don't really need this. I just wanted to give this pointer here. So how does a myopic approach work for this problem of finding the code for a given alphabet? It works as follows. We find the 2 characters with lowest weights. Okay, it says some 2 characters because they might be ties, and in that case we have some freedom. So A and B are 2 characters that have the lowest weight. Say A has the smallest weight, and after A is removed, B has the next smallest weight. Whenever we encode these, the convention is, well, those are very rare characters, so we can assign a long code word. So we can do, those 2 characters are like the most unimportant characters. So the idea is to assign them some long common prefix, U, which is the same for both, and then we add 1 bit to distinguish between A and B. We have to distinguish between them, but we can be generous. We can do a long string for those 2 because they are very rare. Those are the most unimportant characters. Now, once we've committed to doing this, we can conceptually replace those 2 characters by a single one. And this, I used the same graphic notation that we had for the suffix arrays in the last unit. This is to mean we now have a character that really represents a pair of characters, but it's treated as a single unit, and its weight is just the sum of the weights of those 2 characters. By doing this, that means we make the alphabet 1 character smaller, because we remove 2 characters and replace them by a single one. So we can recursively apply the same algorithm on the smaller alphabet. There will be, again, 2 characters of smallest weight. Those will be identified, will be replaced by 1 such super character with the sum of their weights, and so on and so forth. And when this recursive algorithm returns, it will construct a code for, in particular, our character AB, and that will be the U that we use up here. Formally, there's the base case missing. If I'm looking for a code for just 2 characters, I just assign 1 0 and 1 1, and that's it. So you need this this base case. Other than that, this description is all there is to Huffman's algorithm. This is a nice conceptual description. If you think about what's really going on here, you can implement the same algorithm efficiently using a priority queue. So one of those abstract data types back from Unit 2, where we had, for example, the binary heaps as an implementation. So this is an application of this data structure that we covered there. If you initially throw all your characters into this priority queue using the weight as the key, then you can use, in this step, you can use 2 delete min calls. That gives you 2 characters with minimal weight. And then step 2, where you put in this new character, you take you create this new pair character and assign it the sum of the weights, and then insert it back into the priority queue. And that way you can find the smallest characters efficiently. So let's do a quick example how this works. We're given a string, a text, lossless, so it's over the alphabet ELOS. Now the first step is count the frequencies of occurrence in this text. There's 1 E, there's 2 L's, there's 1 O, and there's 4 S's. Then you write down all your characters with their frequencies on top. So in a sense, this is your priority queue. And now you do two extractments. This one and this one are characters with minimal frequency. And you combine them. So you form this super character EO, assign it weight 2. So this whole thing essentially represents this super character EO. And it has weight 2, and the other two are as they were before. So now this is the priority queue. And you again do two deletements, that gives you those two. And again you combine them into this character. And that gives you the EOL character. And now, well, the priority queue really just contains those two, so the only thing you can do is group them. Now, as you can see in this example, whenever we take two things out, I've described here in text that we take some common prefix that we don't know yet, the U, in the code words for A and B, and then there's a single bit that separates them. That's the same as saying in the code try, there will be a node. It's somewhere in the tree, so there's a path from the root to this node that has path label U, but we don't know what that looks like yet. But we know that this part of the tree here has this shape. So we might as well build this subtree and keep it as just an isolated subtree without knowing where in the final tree it will end up. And that's what this algorithm does. It combines those two in exactly that way and keeps this as a subtree. And in the general case, you will always have a list of tries now, really. It's small tries that you combine. They initially consist just of a single leaf, and after the algorithm gets going, it's a larger try. And you combine them whenever you take two new characters, you form a new internal node and just join those two together. That's Huffman's algorithm. That's how the construction of this code works. Now the final outcome is also called a Huffman tree. You might call it a Huffman trie, but people decided it's a tree in this case, so it's the code trie for the Huffman code, and it's called the Huffman tree. Get used to it, I'm sorry for that. That's just how people decided. And well, to finish the example, here's the compression ratio that we achieve for this tiny text. So if you encode lossless with this trie, you would get this string. And if you work out the numbers, the compression ratio is 88%. So it's compressing. Even for this very tiny example, Huffman codes are effective. And so that brings us to the question of how good those codes really are. Before we get there, I want to point out something that will be important for the tutorials or exam problems. The above procedure, this algorithm, Huffman's algorithm, is a little bit ambiguous in the sense that it's not clear if there's several characters with the same minimal weight, which one should we choose? And also in forming the tree, if those there's really a symmetry between left and right in the trie. But I want you to use this tie-breaking rule whenever you construct Huffman codes. Please break ties in tries in exactly this way, and you'll see an example. The slides have an example, and I think I have one on the tutorial. If not, we would put one in the last week. Now the last thing for today is how good are those codes that Huffman's algorithm constructs? I claimed initially that it actually solves this problem optimally, and that's indeed true. So that's summarized in this theorem. Whenever you have an alphabet and some weights, Huffman's algorithm computes a code trie or code words or code word lengths, so that this summing up over all characters, the length of the code word times the weight, is minimal among all prefix-free codes for this input. And in principle, the proof is a simple induction over the size of the alphabet, where you follow exactly the construction of the algorithm. And it's a simple proof by counterexample. I promise this will be the last thing for today. It won't take us long to go through this. Just assume any optimal prefix-free code E star. Now, because this is a trie, there will be two leaves that are siblings and that are at the largest depth D. That's just, no matter how this trie looks like, at some point you will have a deepest node, and so the deepest leaf, and that node's leaf cannot be an internal node, otherwise there would be an even deeper leaf. So you will always find two leaves that are siblings at the largest depth. Now, also, I can always swap characters. If I have a trie with leaves at different depths, I can decide to swap the characters in those two leaves. Now, that will put this one to a shorter code word and this one to a longer code word. So if I do this, I can enforce that those leaves that are at the highest depth contain two lowest weight characters in the whole alphabet. If not, I can swap characters around to enforce this, and the total length of my code can only get better. But if I start with an optimal code, it means I actually have to have those two already in the leaves, or at least in leaves of the same depth. And then if I have this situation, so this is X, this is Y, and they contain those two lowest weight characters, I can replace this whole subtree by conceptually a leaf for A and B, for the combined character. And then any optimal code for this reduced instance yields an optimal code for the big instance by replacing that leaf again by the subtree. So I can use the inductive hypothesis for the recursive call that Huffman's algorithm constructs an optimal tree for this sigma prime, and conclude that by inserting this little tree, we also get an optimal tree for the whole of sigma. So to sum up and conclude for today, Huffman's algorithm computes an optimal code trie given weights for the character symbols, and it does that even efficiently.